Like I said, little earthquakes occur all the time. So yeah, they're definitely on there. And you can go to the TUPA website and you can see our seismograph. It measures magnitude and the duration of the earthquake. But it's part of the East Coast Monitoring Network. So, you know, if you see a vibration at a seismograph, it could be a local thing like a quarry blast or something that is not an actual earthquake source. You need to have the network of seismographs to tell you whether or not the event was seen at multiple seismographs. Then you know both where it's coming from and whether or not it was just a local source or something bigger that came from further away. And of course, you know, the money follows where the big quakes are, and the West Coast has most of the action, and people tend to forget about East Coast seismology. It doesn't occur often enough, which in my opinion is kind of short-sighted, but you know, this is the way things go. So Lamont is doing its best to keep the network going on their own funds while they pursue additional funding sources for it. And so their technician came down and recently serviced our seismograph and got it back online. But yes, it's still up, it's still running, the network is still going while they're trying to assess the future. So although earthquakes on the East Coast are infrequent, they do happen. And they can be reasonably large. You remember the one in Philadelphia like 5 or 6 years ago, they felt actually occurred down in Virginia and cracked a number of structures down there. The East Coast is not an active seismic zone. The major faults are in the Mid-Atlantic Ridge and on the West Coast, but we do have lots of ancient faults that go back to times when this was tectonically active, when Europe and North America collided together and thrust up the Catskill Mountains and all the rest that were at one point as big as the Rockies. You know, this was an active zone, so there's lots of cracks and faults that are left behind from that period. And when there's enough stress on the boundaries of the plates far away, those cracks can occasionally move. And so Boston's experienced major quakes, Charleston's experienced major quakes, you know, and so although they're rare on a human time span, they do occur. And because the crust here is colder and more dense, when you have an earthquake on the East Coast, the waves travel further. And they tend to do a little more damage for the amount of earthquake that you get. Furthermore, our earthquake structures are not resilient. We don't code for them. You can't build a structure in California without designing for earthquakes. We have a lot of old structures that are not designed for earthquakes. And so if you were to get a reasonably large quake on the East Coast, it would probably do a disproportionate amount of damage for the size of quake that you would get. And it's also important just to map and understand the fault structures that are around here. And the problem is because the quakes occur so rarely, the data comes in only very rarely. So it takes a long time to map these faults. You know, the faults on the West Coast are making noise all the time. And so we get all this data to collect on. Ours, like every 5-10 years, they pop up as a little peep somewhere. And so unless you're watching for it, you don't get the data to develop the information on our fault structures around here. It is involved in studying the ancient fault structures on the East Coast and find a map out where these structures are and which ones could potentially liberate earthquake, you know, maybe 100 years from now, maybe 50 years from now. You know, it helps to understand the tectonics and the fault structures on the East Coast. They're basically our only listening devices for what's happening around here. And it's sort of part of that long-term record. Even if it's not an immediate geologic hazard, it's part of developing our understanding of what zones are active and which ones could kick off some energy. Mainly our research has not been earthquake related, it's been seismic related for seismic exploration. I'm an environmental geophysicist. I don't do earthquake seismology for my research, but you can produce your own seismic sources and use seismic energy as ways to image structures. So you can think, if you think of geologists as the doctors from Mother Earth, geophysicists are the medical imaging technicians. We're the ones who do the x-rays, the CAT scans, the PET scans, right? We try and see what's down there without digging a hole. Just as Mother Earth, just as you wouldn't prefer exploratory surgery, you'd rather have an X-ray, Mother Earth doesn't like you drilling, right? So the only way to find out what's down there is either drill or to image. Drilling is very expensive. So, various geophysical techniques are used to image what's down there, usually for, for mineral exploration, for oil exploration, but also for environmental mapping, finding waste sources, so sending seismic waves into the ground to image what's down there is one of the ways to find out what's happening. That's not using earthquake seismology, that's providing your own active seismic source. Now, in many cases, it could be a sledgehammer, it could be an explosive, whatever. You're putting a sound pulse into the ground, and then you're getting the returns from that. So that's the kind of research that Joe Coe and I have been doing. It's seismic, but it's not earthquake seismology. We call it, well, most geophysicists start as physicists because physics is the study of energy and matter. Mm-hmm. You image the Earth by sending energy into the ground, and you look at what comes back out. And so that's what geophysicists do. We try to understand geologic structure by looking at energy into the ground. I mean, one of the things that's interesting to know, for example, where earthquake seismology comes into our understanding and not just hazards. What do you think is the deepest hole we've ever drilled on this planet? The deepest hole we drilled was an exploration hole in Siberia. It's about 18 miles deep. Earth is thousands of miles thick. How do we know that if we've never even drilled through the crust? If you were to dip a globe, an ordinary globe in water, the Earth's crust is thinner than that film of water on the outside. So everything we know about the Earth, we know about through geophysics, through energy that's passed through the Earth and seen on the other side. And one of the best energy sources, if you want to image all the way through the planet, is earthquakes. So when you have a large earthquake on one side of the planet, the earthquake waves go through the entire planet. And seismometers on the other side of the Earth pick those waves up, and it's like having a CAT scan through the planet. So the reason we know about some of these structures down here is because of the energy forms that are sent through the planet. So it's not just, we can think of earthquakes as, yeah, they're a geohazard, they hurt people, but they're also a way that we explore our planet. Because we can't generate a blast as big as an earthquake. Earthquakes liberate this giant pulse that we can see through the planet. So yeah, and the East Coast Network is just part of that overall monitoring network.
Discover more at ambler.temple.edu/scienceofscary.